as of now, you can quantitatively visualize how water molecules behave at the molecular level. Pure water always has few quantities of H₃O+ and OH- ions. Imagine we have pure water and we added some amount of acid to it. For the time being, we will use hydrochloric acid for our better understanding. Hydrochloric acid, or HCl, is a strong acid, and when it is added to 1 liter of water, it gets completely ionized to H+ and OH-. It donates its proton to the water molecules, and the chloride ions are stabilized by the solvation. Now, try to visualize what will happen to the water molecules. For our better understanding, we will try to divide the entire procedure into multiple steps. But in a real scenario, these steps simply do not exist. Earlier, we had 55.5 minus 2 into 10 to the power minus 7 moles of water molecules as H₂O and 10 to the power minus 7 moles of H₃O+ and 10 to the power minus 7 moles of OH-. Let's assume we added 0.01 moles of HCl to it. 0.01 moles of HCl will have 6.023 into 10 to the power 21 molecules of HCl. As discussed, HCl will be completely dissociated in water. In solution, now we will have 6.023 into 10 to the power 21 H+ ions and 6.023 into 10 to the power 21 Cl- ions. The H+ ions cannot remain independently. They have a strong tendency to form H₃O+ by attacking to the lone pair of oxygen. Remember, we already have 6.023 into 10 to the power 16 H₃O+ ions and 6.023 into 10 to the power 16 OH- ions in the solution. So the newly added H+ ions have two preferences. 1. They will protonate the OH- ions and or they will attack the H₂O to form H₃O+. Since the number of H₂O molecules is much higher than the OH- ions. Therefore, the H₂O molecules will get protonated fast to produce H₃O+. Nevertheless, some OH- also gets protonated to form H₂O, but this is a very small fraction as compared to the protonation of H₂O. Now, the concentration of H₃O+ is significantly high in the solution. As a result of which, the equilibrium is shifted towards the left and it suppresses the autoionization of water and reduces the amount of OH- in the solution. Earlier, we had 10 to the power minus 7 moles of H₃O+ and 10 to the power minus 7 moles of OH- ions. Now we have added 0.01 moles of H+ to the system. Now, we will have an additional amount of H₃O+ in the solution. Here it is 10 to the power minus 7 plus 10 to the power minus 2 mole. Since 10 to the power minus 2 is much greater than 10 to the power minus 7, we can write that the total concentration of H₃O+ is 10 to the power minus 2 moles. At the same time, the concentration of OH- ions has been reduced because of the protonation and suppression of autoionization of water. The new concentration of H₃O+ and OH- is such that the thermodynamic equilibrium is maintained, therefore, maintaining the ionic product of water at 10 to the power minus 14. The concentration of OH- now became 10 to the power minus 12 moles. The overall solution now contains 10 to the power minus 2 molar H₃O+ and 10 to the power minus 12 molar OH- ions. The ionic product of water will remain the same, 10 to the power minus 14. Here, I am interchanging moles with molarity because the solution volume is fixed, which is 1 liter. To get the molarity, we will have to divide the number of moles by the volume of solution in liter. In this case, the numerical value will be the same. Now, one question may arise: what happens if we add a large amount of HCl to water? We cannot add an infinite amount of HCl to a fixed amount of water. Solubility and other factors set the limit. In practice, the concentration of aqueous hydrochloric acid is limited to about 11 to 12 molar. This limit is not simply due to solubility, but arises from the equilibrium between HCl gas and water as well as the non-ideal behavior of highly concentrated solutions. Beyond this point, additional HCl does not remain fully dissolved in the aqueous solution. It is important to note that highly concentrated solutions behave differently than the dilute solution. Suppose we prepared a 10 molar HCl solution. That means now our 1 liter of water contains 10 moles of HCl. If we look at the molecular level, 10 moles of HCl is equal to 6.023 into 10 to the power 24 number of HCl molecules. In this scenario, we will immediately have 10 molar H₃O+ in the solution. So, the equilibrium is drastically shifted to the left. And the concentration of OH- will reduce significantly. In theory, the new concentrations of OH- will become 10 to the power minus 15 molar. Though it is a relatively small number, it never goes to zero. But in practice, the concentrated solutions behave differently than the dilute solution. The ionic product of water also changes. In concentrated solutions, we consider the activity of the H₃O+ rather than their concentration in the equilibrium equations. And for very highly concentrated solutions like 10 molar, the activity of H₃O+ differs significantly from their ideal concentration. A similar phenomenon is observed when we add bases to water. Here, the number of OH- ions increases significantly, and the number of H₃O+ ions in solution is reduced. When we say concentration, it means how much quantity is present. But when we say activity, it means how much is effectively behaving. There is a relationship between concentration and activity. Activity of a species is equal to the concentration of the species into activity coefficient. The value of the activity coefficient decides how the particular entity behaves. For dilute solution, activity coefficient is nearly equal to 1. Here, the activity is equal to concentration. But for concentrated solutions, it can be either less than or greater than 1. There it changes the effective concentration. We will discuss the activity coefficient in our next lecture. But for now, it is sufficient to know that because of the activity coefficient, the effective concentration is significantly different from actual concentration in concentrated solutions. This will be useful while calculating the pH of concentrated solutions. While calculating pH for our 10 molar HCl solution, we cannot write 10 in the H₃O+ concentration. Because remember, the pH is not related to concentration. It is related to the activity of H₃O+. And in dilute solution, activity is always nearly equal to concentration.